Start. So this is what today's lecture is all about. Does anyone know what that's called? Like the name for it?
Something inversely related to something else.
John?
Ohm's law?
Yeah, it's Ohm's law. Okay. And this is basically the fundamental law governing how all of your circuits are working. So we have to dissect the components if we're going to understand this. So let's start off with this one. What's that called? Current, right, and it's measured in amps, right? So this is current. What is current?
Like the flow of electricity.
Right, so it's the flow of electricity. And what is electricity?
Like electrons.
Right, so like charges, electrons, they're moving, right? So, to give you an analogy, right? We've got the hallway outside, right? So if you went through here in a circle, like in a circuit, right? Because a circuit, you know, you're essentially it's just going to, in a circle, returning to where you started, right? If three of you pass by every second, right, versus one of you every second, sort of like the current of you is greater, right? There are more of you moving by every second, right? So current has to do with the flow of electricity, and it's how much is flowing. How many charges every second, how many electrons are passing by every second. Does that kind of make sense? Okay. So now let's talk about R. What's that?
Resistance.
Resistance. What's the unit of resistance?
Ohms.
Ohms? Right. That means ohms. And let me just put up an A here for amperes.
What does ohms stand for?
Ohms? It's just ohms. That's the Greek letter omega. But ohms is just the unit for resistance. Not sure if it stands for anything. I guess like because this is omega. So what is resistance? Anyone have a functioning definition of it? Good idea? Yeah?
It makes the current not want to flow as much, like it makes it like stop.
Exactly, right? So remember how we were saying that current is how many charges are passing by in a given time. Resistance is what tries to stop them, right? So let's go back to the hallway analogy, right? Let's say that there are three of you who want to run through the hallway, right? Let's say that I make the hallway a lot more narrow. Now instead of all three of you running side by side, you're probably going to have to run behind each other. So not as many of you can pass by every second, right? You're sort of more staggered, and you can't move as quickly. There's not as much room, right? On the other hand, you know, if I make it wider, now more of you can push by every second, right? Or however much, you know, whatever your unit of time is. So resistance is essentially telling you that, you know, something is trying to stop the current from flowing. Current is the charges moving by, resistance is what tries to stop them. And remember how I was just telling you that the area matters? Resistance we can actually get from a formula right here. So this is length, and this is area. So in your circuits, what typically provides the resistance? What component? Exactly, resistor, right? So resistors, if you put more of them on in a sequence, what's going to happen to the resistance of the circuit? If you line them up.
Well, the resistance will increase.
Yeah, the resistance is going to increase because now they have to pass by more of these resistors, right? It's like if I made the hallway longer, you guys are going to like run out of energy, so you know the current's going to go down because not as many of you guys are going to be passing by as quickly. Does that kind of make sense to everyone? Any questions about that? If you have questions at any point, like just raise your hand.
Wait, how does the length and area part like relate to that?
Okay, right. So first of all, this guy right here, this is the Greek letter rho. It's resistivity. So each material has a different resistivity. It's the difference between me taking a battery and putting a wire from one end to the other, and me taking a battery and putting paper from one end to the other. Wire has much lower resistivity, so charges can move much more quickly. Paper has extremely high resistivity, so charges aren't going to move as easily. But once we know the resistivity, we have to look at the length of that material and its area, right? So like you just said, with resistors. If we line them up, right, if the resistor becomes longer, its resistance is going to go up. On the other hand, if it becomes wider, you know there's more room for charges to flow through. So that means the resistance is going to go down. That's why it's in the denominator. Because if this number gets bigger, this number gets smaller. That makes sense, just mathematically? Okay, great. Okay, last part. V. What's that? Voltage. And what is the unit of voltage? Volts. It's an easy one. Some people, they draw with these little bars on top. Volts. I think I mixed up the order, so whatever. You know what I mean. This is the symbol. This is the unit. What is voltage? Any idea of it? This is probably the toughest one. Yeah, Vincent?
Like the pressure pushing behind it?
That's a really good way to think of it, right? If we go back to the hallway analogy, you know, there's got to be something pushing you guys through that hallway, right? If I'm, you know, if there's a stronger push, right, then more of you can get through, right? Another way you can think of it is like how much energy you all start out with, right? So let's say that there's like, you know, a big pile of candy here, right? You all eat it up, you get a sugar rush. If you all have like a bunch of energy, you can easily, you know, run through here, right? More of you are going to be able to run through here. But if I just lay out one Snickers bar on the table, you know, maybe that's only enough for like 1, 2 if you share. I would never share, you know, to get through the hallway, okay? So voltage is basically like the push, or the initial energy that I give you, right? So you're going to use up all of it by the time that you get back to where you started. So it's going to determine, you know, given how wide or long the hallway is, the resistance, right, length and area, how many of you will be getting back, you know, how many will be getting through at a time? Does that sort of make sense in terms of voltage? This is definitely the most difficult part of Ohm's law, so I really want to hear questions if you have them. Okay, we're going to come back to this, so don't worry about it. So now, let's talk about why this is relevant in your circuit. Right? Because it's like, great, I know what my voltage is or my current or my resistance, like why does that matter? Why does that do things? Here's another equation. What's that?
Watts.
Watts. Okay, watts, power, exactly. So this is power, and it's measured in terms of watts. What's a watt? What's a watt?
Joules per second.
Joule, yeah, exactly. And what's a joule?
Energy.
Energy. So this is telling you how much energy is being given off every second. Haha, Randy. Everyone heard that. It's okay. It's fun. So this is telling you how much energy is being given off per second, right? Because you're giving off energy as you go through your circuit, right? When you're going through the hallway, you know, you're going to get hot. And if there are more of you, and you're more energetic, you get even hotter and sweatier and probably smellier. So that makes sense, because it's saying power is equal to IV. Because what did we say current was?
Like how many electrons are moving through in a second.
Exactly, right? So this is like how many of you are. And what did we say about voltage? What that was?
Like the initial energy or push.
Right. So if there are more of you and you're more energetic, right, you're going to be giving off more energy, right? You're going to be hotter and sweatier, like I said. So as you're running through that hallway, you know, you're going to be giving off a lot more heat, a lot more energy, okay? So now let's bring it back to circuits, right? Because we now can see that a circuit element which has a voltage across it and a current is going to be giving off energy. Can you guys think of examples of circuit elements, right? So things that you put in your circuit where you've seen forms this, right? Where you've seen energy being given off.
Never mind.
No, go ahead. What were you thinking?
Resistors.
Exactly, right? Resistors, they give off heat, right? Have you ever had a current across a resistor for a long time? You touch it, it gets kind of hot. So now that's giving off heat energy because of the power. What are other examples? Come on, you guys have built some incredible circuits already. What have you put into them? Eliana. What was your STAR project?
A Larson scanner.
A Larson scanner? And what did it do?
It was just like a light show.
It was a light show, right? So, what in that, like, what was like the most sort of like, you know, really obvious example there of like energy being produced or given off? Like, what in there was kind of like this is what's happening? Like, what was
What do you mean, like the resistors, I guess.
the resistors, right?
And then the capacitor had like all the electrical.
Uh-huh. What did you see when you like turned that on?
Like the light on that.
So isn't like it giving off light a way of it giving off energy?
Yeah.
So you put a voltage across it, it has a resistance, there's a current, you multiply that current by the voltage, right? That's telling you how many electrons are moving across, the energy they have, and they create light. And next week, I think Randy, he's going to give a lecture on diodes and LEDs, and he's going to explain more about how that works, right? And how LEDs, they turn voltage and current into energy in the form of light. Does that make sense? What are some other examples? What about a speaker? Anything else?
Wait, I have a question.
Yeah.
Why are diodes like different from this kind of category?
Okay, so why are diodes different? It's because they're semiconductors, which is this weird sort of manufactured material where the voltage and current have like a very sort of like similar
What's the
relationship.
direction or something?
Yeah, direction's definitely involved, and there's also some cool like chemistry stuff going on there. Like, it's gonna be a really fun lecture. Okay. All right. So, do you have any questions right now about power? Anything? Okay. So, we cool if I erase some of this? All right. So I'll just erase this part. Alright, let's do a bit of review, right? So, let's go back, just once more. We know that your voltage, which is what? Anyone? Exactly, right? Your current, which is what?
Flow of electrons.
And your resistance, which is?
Limits to the current kind of.
Right? They're all interrelated. And we learned the equation for that. So let's solve a few problems. Does anyone know what this is? Right. What's this? Okay. So let's say that the voltage across here is 6 volts. And let's say this resistor has a resistance of 3 ohms. What's the current flowing through this circuit?
2 amps.
Who said that? Nice. Yeah, so it's 2 amps. Why is it 2 amps?
Because V over R equals I, so 6 over 3 is
Right.
2.
So we start out with V equals IR. We know V, we know R, we want to solve for I. So we just divide by R, this cancels, and then this becomes V over R is equal to I. V was 6, R was 3, that's 2 amps current. Okay, any questions? Let's do another example. What's going on here in this diagram? Yeah? Yeah?
A current flowing through the resistor.
Right. Current of 3 amps and a resistor of 5 ohms, and it has the current flowing through it. What's the voltage across this?
15, what's the unit again?
Can you remember?
Oh, just volts, yeah.
Right, exactly. So there's 15 volts across this. And again, it's V equals IR. I, the current, was 3. R, the resistance, was 5. So that's 15 volts. And now, we solve for the current. We solve for the voltage. Can you guess what we're going to do next?
Solve for resistance.
So, say the voltage across here is 10 volts, and the current running through here is 2 amps. What's the resistance of this?
5 ohms.
Yep, 5 ohms. Because V equals IR, and this time we want to solve for R, so we just divide both sides by I. So we have V over I is equal to R. That's V is 10. I is 2. That's 5 ohms. So, does anyone have any questions right now, like on anything to do this?
Why do you need to know, like, if you know what the voltage is, why does it matter what, like, the resistance or the current is?
Right. So, the best explanation of that probably is this, right? Because we can know the voltage, right? That tells us the initial energy, right? But we need to know how much we're being pushed back, right? Because if we can only send through 1 electron at a time, it's not going to be giving off as much energy. Even if we gave a whole bunch, 10 electrons at a time going through would be giving off a lot more power than 1 at a time. So this is one of the big reasons why that matters. Power is equal to current times voltage. And remember that current is determined by the resistance. In fact, we can write this in a few other ways. If we have P is equal to IB, and we have V is equal to IR, if we substitute this into this equation, what do we get?
V equals I squared R. P equals, yeah.
I squared R. So here we can see that if we know the current, right, we still don't know the power unless we know the resistance, right? What if we want to substitute, so say we want to do V over R is equal to I. If we substitute I back into this, what do we get?
V squared over R.
Right. So power is equal to the voltage squared over R. So Hadassah, if we know the voltage, we still need to figure out what the resistance is to determine the power. And this is going to tell you the power, you know, how much energy your LEDs are giving off, how much energy in the form of sound your speaker is giving off, or how much energy in the form of heat your resistor might be giving off. That was a good question though. Does anyone have any others? So everyone's telling me everything made what?
How do you figure out the voltage across the resistor?
How do you figure out the voltage across a resistor?
Yes.
You would need to know the current through it and its resistance.
So I hook it up in a circuit,
Yeah.
and I want to figure out what the voltage drop across the resistor is.
Okay,
What do
so
I do?
tell me how the circuit looks.
Just the battery connected to
To a resistor?
To a resistor. What tool?
Oh, what tool do you use? Good question. Anyone know what tool you use? Voltmeter. And here we have something that encompasses a voltmeter as well as a couple other tools. What's that called? Digital multimeter, right? Does anyone know how to use, in this configuration, how would we use the voltmeter?
You have the two, what do you call it, the probes,
and then you touch one point before the resistor and the other point right after it.
So here's my voltmeter. And this would tell me the voltage across it. So that means that even if you don't know the numbers, you can use the digital multimeter, you hook it up like this, and you can find the voltage across it.
What about the current?
Good question. So what if I want to find the current that flows through this circuit? What should I do?
Put an ammeter.
What?
Put an ammeter.
Put an ammeter. Where do I put it?
You like disconnect a part of the circuit, I guess, and then like you attach it right in between, like just like it's one point on the circuit.
Why do I do it like that and not like this with the voltmeter?
Because otherwise you would short it.
Right, because what's the difference between ammeter and a voltmeter?
Ammeter, the resistance is much lower. So if you connect the 2 points, the circuit is going to run through the least resistance, so you're going to burn it out.
Yeah. So the important thing is, if you're measuring the voltage, you put it in this configuration, which is known as parallel. And if you're measuring the current, you put the digital multimeter in this configuration, which is known as series. Can I also use the multimeter to find the resistance? Yeah? How do I do that?
You just put it across the resistor in the circuit. Put it across the resistor.
I just take the resistor
Yes, that's good.
and just take my ohm meter.
But not while it's broken, right?
Just do that. Yeah, generally we want to do it like this. Any other questions on this? I'd be amazed if everything sunk in after just this lecture, so you guys have got to have some questions.
So that one isn't connected to a circuit?
No. Because the way that it works in this configuration is that this is actually sending, a small current across this, and then it measures the voltage across that. And using Ohm's law, it actually determines what the resistance of it is. Other questions?
So confused on why the voltmeter goes beside the resistor and why the
Right.
amp meter goes like inside.
Okay, so current always wants to take the path of least resistance, right? In fact, let's talk about parallel circuits first, and I'll help you understand it better. So, okay. So if I have two resistors like this, right, and hook them up to a battery, what's this configuration called?
Series.
Series. Good. And what is the, if this has a resistance of 4 ohms and this has a resistance of 3 ohms, what's the total resistance in the circuit? 7 ohms. What if I do this? What's the total resistance in this circuit?
5 over 2.
I'm not good doing math in my head, so let me do it out and then I'll explain.
Just 5.
So 5 ohms. Okay. Why is it like this? Kind of crazy, right? Any ideas? Like, any idea why it might look like this instead of just adding them together? Like, what's different about this versus this? What does the current have to do in this circuit? In this circuit, the current starts here, right? It goes through, and it has to pass through both of them, right? In this one, doesn't the current have a choice? Right? So that means that there's actually oddly enough less resistance than 10 ohms because now there are 2 paths. It's like if I put 2 hallways out there. So at first, if there's just 10 ohm resistor, right, 1 hallway, maybe only 5 of you could fit through at a time. But the second I place a second one out there in parallel, so it's like a second choice, now twice as many of you can fit through. As a result, the resistance is halved. There's less resistance impeding the current flowing through. So let's go back to the question of why does it matter that you're putting the voltmeter in parallel? The voltmeter has extremely high resistance, really, really high, right? So if I put the voltmeter in series, like this, so here's this, and I take the voltmeter, right? And let's say that its resistance is like 1 million ohms, which is the same as 1 mega ohm. What's going to happen to the current in this circuit? It's going to go way down, like almost nothing there, right? On the other hand, if I put it like this, does that really change the current much? Because sure, it's another path, but it's such a tough path that it's barely going to affect what's going through here, right? So if I don't change the current, that means I'm not changing the voltage across this. So a tiny, tiny, tiny amount of current still gets through to here, but this is sensitive enough that it can still read the voltage with that signal. Does that make sense why we do it that way?
Wait, does the voltage add a current?
Does the voltage add a current?
I mean, the voltmeter.
So you're saying does it increase the current here?
Like if it's adding like the current.
Like to the circuit, whether like, so because like it's another path, a tiny amount of current will be added to the circuit. But it's so small that it really doesn't affect it that much. Okay. Does that make sense? Good? Do you think this will be helpful with your projects? Understanding them, putting them together? If you have any questions about this, ask me, other instructors.
Good job.
Yeah.